Hi, this is Simon Apers. I'll be talking about the quantum complexity of minimum cut, which is joint work with Troy Lee. We'll be talking about weighted graphs with vertex set V, edge set E, where n will denote the number of vertices and m will denote the number of edges. We'll also assume that the weights are non-negative. A cut in the graph is a set of edges C such that G minus C is disconnected, and the minimum cut value in G is equal to the weight of a cut with minimum total weight. Is equivalently defined as the minimizer of W of C, where C goes over all cuts in the graph. And again, equivalently, it's equal to the minimum weight over all vertex subsets of the weight of the outgoing edges from S to S complement, which always represents the cut in the graph. So the minimum cut of a graph and the complexity of finding this minimum cut is a fundamental problem in both graph theory and combinatorial optimization. And there's a very long line of research starting from the 1960s, where the first polynomial algorithms were designed by people such as Ford Fulkerson, Gomori, Hu, and others. Went on through the 1990s, where Carter proposed the first near-linear time algorithm. So this is near-linear in the number of edges of the input graph, where the tilde hides polylog factors. And it goes on until today, because only a couple of months ago there was a large breakthrough by Jason Lee, who showed the first deterministic near-linear time, or at least almost linear time algorithm for minimum cut in weighted graphs. In this work we study the quantum complexity of minimum cut. That is, what is the complexity of solving minimum cut on a quantum computer? Now, what do we mean by minimum cut? On the one hand, we'll be talking about the quantum query complexity of minimum cut, which is the total number of queries that a quantum algorithm or quantum computer has to make to the input, which is a graph in this case. While this is often trivial for classical algorithms, so for instance, it's not so hard to prove that finding the minimum cut of a graph requires a number of queries to the input, which is at least as large as the input. So basically, we have to query all edges of the input graph. But for quantum algorithms, we can often get a sublinear query complexity. A very classic example here is that where we want to find, we want to determine the OR function on an input bit string x. So basically, we want to determine whether there exists a bit which equals 1. Classically, we need to make a number of queries which is linear in the size of the input, whereas quantumly, we only need to order square root n queries by using Grover search. For graph problems, unfortunately there are two sort of input models that make sense. On the one hand, we have the adjacency matrix model, where A represents the adjacency matrix of the input, and entry ij has weight wij, which corresponds to the weight of edge ij. And the query here consists of inputs I and j, and we get back the weight of edge ij. So we'll assume that if there's no edge, then we just return weight wij equals 0. And then alternatively, there's also the adjacency list representation, which you can think of as a sparse representation, where every vertex basically stores a list of its neighbors with corresponding edge weights. The query here takes the form ik, where I is a vertex, k is an index, and we are returned the kth neighbor of I and the corresponding weight wij. Alternatively, there's also the quantum time complexity that we'll talk about, which is always lower bounded by the query complexity. Basically, it also takes into account all other operations apart from queries that you have to make. So it equals the total number of elementary gates, queries, and QM operations, where QM operations are basically operations where we access a classical or at least we access a large memory, which we can classically modify, so we have classical write access to this memory, and we can coherently make, at least we can make quantum queries to this memory. This is an assumption that is often necessary in quantum algorithms for graph problems. An example of the quantum complexity of a graph problem is connectivity. So the question, is graph G connected or not? So we basically want to distinguish the left situation from the right situation. It was shown by Duur, Heiligman, Heuer, and Mala in 2004 that the quantum query and time complexity of connectivity is scales with n to the 3/2 in the matrix model, and scales with n in the list model. So there really is a distinction between these two models, which is important. And notice that solving the minimum cut of a graph is at least as hard as determining whether it's connected or not. Because if the minimum cut is 0, then we know the graph was not connected, whereas if the minimum cut is larger than 0, then the graph must have been connected. So we know that these bounds also give lower bounds for the quantum complexity of minimum cut. Namely, we find lower bounds n to the 3 over 2 in the matrix model and n in the list model. So let's talk about some quantum query bounds for minimum cut apart from these first. Namely, we want to talk about what are the limits of quantum speedups. Consider the following elementary quantum query complexity problem, where we're given quantum query access to an arbitrary 0-1 matrix now, where entry ij holds bit xij, which is either 0 or 1, and we want to determine the Hamming weight of this input, basically the sum of the number of ones in the input. Then was shown by Beals, Burman, Cleave, Mosca, and de Wolf in 1998 that exactly counting this number of ones requires a number of queries that scales with the size of the input. So there's no quantum speedup for exactly counting the number of ones in a 0-1 matrix. Now notice that this implies an immediate lower bound for minimum cut, because consider the following input graph on the left side, which is basically take a bipartite graph where every vertex on the left, vertex I on the left, is connected to vertex j on the right, if and only if xij is equal to 1. Then we add cliques on the left side and on the right side with weights alpha which are much larger than 1. So by adding these weights alpha, we ensure that the minimum cut will never separate left vertices or separate right vertices, and the minimum cut will always be localized exactly through the middle. This implies that the minimum cut, the value of the minimum cut, is exactly equal to the Hamming weight of the aforementioned Boolean matrix X. Namely, the adjacency matrix of this graph looks like this on the right, where we have these diagonal blocks which contain very large elements, so we never want to cut through them. And so the cut basically separates the left side from the right, and the cut value will be equal to the Hamming weight of this diagonal block here. So by the lower bound from the previous slide, we know that there's also a similar lower bound for minimum cut. And so in principle, in general weighted graphs, we cannot find a quantum speedup for determining the minimum cut of a graph. However, there are loopholes. One of them is the approximate counting loophole. It was shown by Brassard, Hoyer, Mosca, and Tabb that we can actually get a quantum speedup if we're satisfied with an epsilon approximation of x. This implies that while we cannot get a quantum speedup for exact minimum cut, there might be a quantum speedup for approximate minimum cut. And this is exactly what I showed in a former work with Ronald de Wolf. Namely, we showed that there is a quantum algorithm for epsilon approximating the minimum cut of a general weighted graph in time n to the 3 over 2 divided by epsilon in the matrix model and square root mn over epsilon in the list model. We achieve these speedups by basically constructing a faster quantum algorithm for graph sparsification, which is something that I'll come back to later. There's also a second loophole, which I'll call the small counting loophole, which says that provided the Hamming weight of x is small, we actually can get a quantum speedup for exact counting. Namely, if we promise that the Hamming weight of x is at most k, then we can exactly compute x by just using Grover search to find all the ones in x. This requires order square root n squared times k, where n squared is the number of entries and k is the number of non-zero entries. So this raises the question, is there still hope for a quantum speedup for minimum cut, provided that there are only few edges? And this is something that we'll also exploit later on. So let me first, as a preliminary, talk a little bit about this quantum algorithm for approximate minimum cut, which is a former work. It builds on the theory of graph sparsification. So given a weighted input graph G, a epsilon cut sparsifier H is a subgraph of G that is potentially reweighted, such that H is sparse, so it only has approximately n over epsilon squared edges, whereas the input graph can have as much as n squared edges. And secondly, the cuts in H approximate the cuts in G. So for every vertex subset S, the weight of the outgoing edges epsilon approximates the weight of the outgoing edges of the same cut in the original graph. Now notice that this implies that in particular the minimum cut of H approximates the minimum cut of G, so that once we have the sparsifier H, we can actually solve minimum cut on H and find an epsilon approximation of the minimum cut on G. And this is exactly what is done in this work, namely what's shown is that there is a quantum algorithm for constructing an epsilon cut sparsifier H in time scaling as n to the 3 over 2 divided by epsilon in the matrix model and square root mn over epsilon in the list model. And it's also shown that this is optimal. Let me also mention that there's a stronger notion of spectral sparsifier, and in fact the quantum algorithm constructs a epsilon spectral sparsifier, again, which is a stronger notion than a cut sparsifier. In particular, this implies the following corollary. There is a quantum algorithm for epsilon approximating the minimum cut in a weighted graph in time n to the 3 over 2 divided by epsilon in the matrix model and square root mn over epsilon in the list model. The algorithm is the following. Given access to the input graph, we first construct a sparsifier, which now only has O tilde n over epsilon squared edges, and then we just use a classical algorithm to solve for a minimum cut on the sparser graph. Since classical algorithms can run in near linear time in the input size, which in this case would be n over epsilon squared, this just adds to the complexity, but this will always be dominated by the cost of constructing the sparsifier. So in the end, this cost here would be the dominant cost for epsilon approximating the minimum cut. And this is a tool that we'll also be using in our quantum algorithm for exact minimum cut, but it is a quantum algorithm for exact minimum cut in simple graphs. So why is that? What we do here is in our algorithm, we exploit the small counting loophole. Namely, if there's only a small number of non-zero elements, then we can actually find a quantum speedup for exactly counting the number of non-zero elements. Then what we use, one of the key ideas is that simple graphs have a small number of edges in minimum cuts, something that I'll elaborate on later on, and then we can find these edges using a graph sparsifier and Grover search. First, let me focus on the query complexity. So this first statement, let me come back to that, says that simple graphs have a small number of edges involved in the non-trivial minimum cuts, where non-trivial means a trivial cut is one that just separates off a single vertex, and it's typically minimum cut problems can be divided into first checking these trivial minimum cuts and then looking for the smallest non-trivial minimum cut. So in some sense, the first problem is very easy, so we just focus on finding the non-trivial minimum cut. So what Kawarabayashi and Torup in 15 showed is that simple graphs, which are graphs that are unweighted, namely all edges have weight 1, and there are no parallel edges, these have a small number of edges involved in the non-trivial minimum cuts. If we go back to the former example where we had this bipartite graph with cliques on the sides, if alpha is very large, then we know that the minimum cut should go through the middle, and if there's many edges in the middle, then the minimum cut can involve up to n squared edges. However, if we impose that alpha is equal to 1, namely the graph is simple, then notice that a trivial cut here, namely just cutting off a single vertex, has a cut value at most n minus 1, because there are at most n minus 1 weight 1 edges leaving that vertex. So that means that if we still want that the minimum cut slides through the middle, cuts through the middle, then we can only put at most, we should put less than n minus 1 edges in the middle. And this implies that we cannot hide some scaling with n squared bits in the middle and ask that the minimum cut has to find all of these. No, in simple graphs we can only have less than n minus 1 edges going through the middle. Well, it is a kind of simple observation that since the trivial cuts have value at most n minus 1, any other minimum cut can also only have n minus 1 edges involved. What was non-trivial is to show that in fact, if you look at the full set of edges that are involved in a minimum cut, so a graph can have many minimum cuts, all of these together, there's still at most n minus 1, or at least order of n edges involved. Somewhat more specifically, I'm talking about the following theorem by Kawarabayashi and Torup and slightly improved by Rubinstein, Schramm and Weinstein from 18, which says that for simple graphs, there exists a partitioning of the vertices into sets P1 until Pk, such that the number of edges that go between the partitions, namely the number of edges that have endpoints in different partitions, is only order of n. there's only order of n edges between the partitions. And second is that these partitions respect all non-trivial near minimum cuts. So that means that if we look at any near minimum cut, by near minimum I'll mean a cut of value at most, let's say 1 plus 1 over 10 times the minimum cut value. So these are cuts that have a value slightly above the minimum cut. Then all of these are respected by the partition. Namely, they will never cut through a partition, they will always cut between partitions. So basically these are cuts like the red ones indicated in this figure here. So this gives us the following sketch of a quantum query algorithm. Namely, in the first step we construct the KT partition of the input graph. This is just a partitioning of n vertices, so we can write this down in order n. I'll leave aside for this moment what the query complexity is of this step. Then the second step, we can use Grover search to search over the full set of edges to just find the edges that are between the different partitions. We know that there's only order n of them, so in the matrix model we search for n elements among n squared elements, so we get complexity n to the 3 over 2. In the list model we search for n elements among m elements, so we get complexity square root mn. And this allows us to basically do the following. What we can do now is we can contract all these yellow components here into a single vertex. This gives us a multigraph or a weighted graph, and since we found all the edges between the partitions, we can also say how many edges there were between the contracted vertices. And now we can just solve for the minimum cut of this contracted graph. And since the minimum cut respects this partitioning, we know that the minimum cut will be found this way. And so this is what we do in the last step. We just find the minimum cut of this contracted graph. And if we only care about query complexity, notice that this requires no queries because we explicitly wrote down this contracted graph. We need to do no more queries to the input graph. And by the Kawarabayashi-Torob partition properties, we know that the minimum cut that we find that way is a minimum cut of the original graph. But of course I left aside what the query complexity is of finding this KT partition. First consider the following very naive and greedy algorithm, namely just iterate over all possible cuts in the graph, and whenever the cut is near minimum, then you slice through the graph along that cut. So basically, let's say that the first cut, near minimum cut that we encounter is P1, P2. We slice through the graph along that cut. Then we iterate over the remaining set of cuts. We find another one and we again slice through it, and so on and so on. And so we get a partitioning, which in the end, it's not too hard to show, is equal to the KT partition, or the Kawarabayashi-Torob partition. Of course, this is much too costly because we basically have to iterate over all possible cuts and evaluate all of these possible cuts in the input graph, which is much too costly. So we have to be a bit smarter, and what we can notice is that the cut values in G are actually approximated by the cut values in a sparsifier H. This is basically how we define the sparsifier. But this implies that the KT partition of H will actually approximately be equal to the KT partition of G. And in fact, we can show that this approximately equal is sufficient for our purpose. So what we can do is the following. In the first step, we can construct the sparsifier H of G, whose query complexity we can bound by O tilde n to the 3 over 2 in the matrix model, or square root mn in the list model. Now we construct the KT partition of H in this sparsifier. Again, since we can explicitly write down this sparsifier, we make no queries to the sparsifier. This step requires no queries. We can just run the naive greedy algorithm. Then again, once we have the partitioning, we can find the order and edges between the partitions using Grover search. And finally, again, without making any further queries, we can solve for the minimum cut on the contracted graph. Let me also add that this rough scheme was inspired by and follows the blueprint of a cut query algorithm from Rubinstein, Schramm, and Weinberg, where they roughly follow the same steps, but they use these steps to construct a cut query algorithm, which is a different type of query complexity algorithm. What we proved now is the following theorem, namely the quantum query complexity of a minimum cut in simple graphs is O tilde n to the 3 over 2 in the matrix model, but recall that we also had an omega n to the 3 over 2 lower bound by the connectivity lower bound, and in the list model we get a square root mn upper bound, and we have this omega n lower bound from connectivity in the list model. So there's still a remaining gap there that we weren't able to resolve in this paper. In fact, we now have this dichotomy that on the one hand, in simple graphs, we can find a quantum speedup, whereas in weighted graphs there's no quantum speedups. The reason is that in simple graphs there's only n edges involved in a minimum cut, while in weighted graphs there can be up to n squared edges involved in minimum cut. And by counting lower bound, we know that there can be no quantum speedup in that setting. What we proved, in addition to what I mentioned before, is that we can actually refine the KT partition result and state that if a graph has edge weights between 1 and tau, so if tau is 1, we have a simple graph. If tau is unbounded, we have a general weighted graph. But if we have this upper bound tau, then there are ordered tau n edges involved in its near minimum cuts. So if tau is constant, then there's still only order of n edges involved. But if tau scales with n, let's say, then there can be up to n squared edges involved. And building on this lemma and the blueprint of the algorithm that I mentioned before, we get the following corollary, which is like a fine-grained complexity bound on the quantum query complexity of minimum cut, stating that if the input graph has weights wij between 1 and tau, then the quantum query complexity of minimum cut is scales with n to the 3 over 2 times square root tau in the matrix model and square root mn tau in the list model. And we also prove a new lower bound, which is tau n in the list model, which is again not closing this gap yet. So that's what I want to say about the query complexity. Now let me talk a little bit about the time complexity of a quantum algorithm. If we go back to our algorithm and we look at the time complexity of the algorithm, notice that the first step, constructing the sparsifier H, can be done time efficiently. Namely, this was proven in the paper by Appers and de Wolf. The third step is just Grover search, so again this is time efficient, and the final step we can just use a classical efficient minimum cut algorithm such as Karger's to also solve this step efficiently. That means that the only step that we have to solve in a time efficient manner to get a time efficient way algorithm is constructing the KT partition of H, where H is a sparse but weighted graph. So we have the following question: what is the time complexity of constructing the KT partition of a sparse but weighted graph? There is the following result by Kawarabayashi and Tor, which they proved in their original 15 paper. Namely, they proved that there is a classical algorithm that finds the KT partition efficiently if the graph is simple. So while this is a nice result and it's sufficient for their purpose, it's not sufficient for our purpose because H will be weighted even if the input graph is simple. A sparsifier of a simple input graph will in general still be a weighted graph. And so we have to do some more work. What we show in this paper is that there exists a quantum algorithm that finds this KT partition for weighted graphs in time scaling with n to 3 over 2 in both the matrix and the list model. So this gives us a time efficient implementation of this KT partition problem in the matrix model but not in the list model. And so I'll also hint at some follow-up work that I did together with Pavel Gavričovský and Troy Lee again, where we actually improve this algorithm. We use the ideas from the quantum algorithm to basically find a faster classical algorithm that finds the KT partition for weighted graphs in time scaling with n squared in the matrix model and m in the list model. So basically we extend the Kawarabayashi-Thorpe result to weighted graphs. And combining this with a quantum sparsification algorithm, we actually find a quantum algorithm for weighted graphs which scales with the complexity bounds that we want. Let me elucidate a little bit what is behind these time efficient algorithms. Specifically, I'll elucidate how a classical algorithm for KT partition would look like in our case. The key ideas are tree respecting cuts on the one hand and generating sets for KT partition on the other hand. So what are tree respecting cuts? Consider an input graph G and a spanning tree T. We say that a cut through the graph G 2 respects T if it cuts at most 2 edges of T. So we see that this cut here contains exactly 2 edges of T, so it 2 respects T. What Karger showed is that if we take an appropriately random spanning tree, so this is not a uniformly random spanning tree, it's a random spanning tree which is constructed through packing, so it's a slightly more non-trivial, but it can still be done efficiently. if we sample such a random spanning tree, then with large probability the near minimum cut, or any near minimum cut, will 2 respect t. Now notice that this reduces the potential number of cuts that we should consider from exponential in the size, namely the set of all cuts, to just those that 2 respect t, which is at most n squared. So we find this better greedy algorithm for the KT partition. Namely, we just iterate over the order n squared cuts that 2 respect t. This significantly exponentially reduces the set of possible cuts that we should consider, and it's a very, very useful tool that Karger also used in his near linear time classical algorithm. But for us, it's still not efficient enough because we can't afford to explicitly go over all these order n squared 2 respecting cuts. So instead, what we prove is we show that instead of looking at this set of order n squared edges, there's actually a smaller generating set of only order n 2 respecting cuts, so that if we slice along these order n cuts, then we actually get the KT partition. So any additional near minimum cut will just slice along the partition that we already have, and so it won't add anything. So we just need to find this smaller set of only order n 2 respecting cuts. So we exactly characterize the set, and then we show how to find, so in this work with Troy Lee, we show how to find this smaller set using a quantum algorithm with time complexity scaling with n to the 3 over 2. And in this follow-up work, we improve this to square root mn in the list model and basically linear in the input size in the classical case. This implies the following theorem. Meaning we can construct the KT partition of a weighted graph in time, again, O till n to the 3 over 2 in a matrix model, and this was is then improved by this follow-up work. As a corollary, we find a time-efficient algorithm for minimum cut. Namely, we show that there is a quantum algorithm for finding a minimum cut in a simple graph, just time complexity, scaling with n to the 3 over 2 in a matrix model, which is optimal, and scaling with square root mn in the list model. We can also use this time-efficient implementation to implement our more fine-grained algorithm, and basically find that if the graph has weights wij between 1 and tau, then the algorithm has time complexity scaling with n to the 3 over 2 times square root tau in a matrix model and square root mn tau in the list model. So all these bounds basically equal the query complexity bounds that we proved earlier. So with that, I'd like to summarize and conclude. Namely, we characterized the quantum time and query complexity of minimum cut. What we showed is that so it was already known through former work that approximating the minimum cut of a weighted graph can be done in n to the 3 over 2 over epsilon the matrix model and square root mn over epsilon the list model. We show that for simple graphs, we can actually, in approximately the same complexity, we can actually find the exact minimum cut. And for weighted graphs where the weights are bounded between 1 and tau, we actually get a fine-grained complexity, which shows that if tau is very large, then we cannot find a quantum speedup, but if tau is not too large, then we can actually find a quantum speedup. The key tools that we used were graph sparsification and this idea of a Kobayashi-Thorpe partition. So with that, I'll conclude, and I'll thank you for your attention.